Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. This is my lecture about the course of nanophysics and technology, having the course code of PHY445. In this lecture and in some series of lectures, I will discuss the properties and applications of semiconductor nanostructure. This is a really vast topic, so it will take some lessons. But in this lecture, I will briefly discuss the general properties and some of the application of semiconductor nanostructure. Later on in the upcoming lecture, I will discuss separately the electrical, magnetic and optical properties of semiconductor that has been drastically improved by changing the size of particle size of the semiconductors. So actually, if you see nanotechnology or nanomaterial have very interesting property, and it had a wide range of application in various fields of life. If you come across the nanoparticle, it has been widely used in catalysis. It has been used in energy in photovoltaics, photonics and hydrogen storage. It has been used for creating new sources of energy, water splitting and environmental cleanup. Similarly, water splitting is used for the creation of hydrogen from water. The same nanoparticles are widely used in electronic and magnetics because of wide range of application, and this has been used in national security, in which include detectors and biocides. Similarly, it is used in environment, that is actually the geosciences and wastage storage and contaminant transport and atmospheric chemistry. The same nanoparticles are used for self-cleaning glasses, or maybe for cleaning the water that is coming from the industries, and using solar light. That is the degradation of inorganic material with the help of nanomaterials. And in same way, these nanomaterials and nanotechnology is used in oxide nanostructures that have hard soft interfaces. So these are some of the applications of the nanomaterial. The small particle and nanostructures have impact in each field of life, and it is widely studied due to its interesting applications. Physical property of nanomaterials drastically change by changing its size. Why the property change? This is a really interesting question, but it is differ from material to materials. Normally, we say that some unusual properties are found when the size or the grain size of the material is reduced. So some of the properties are known, but more property will be introduced when we and discovered when we go through the different morphology of the materials. So this increase in improvement in the physical property of the material may be due to the large fraction of surface atoms, or it may be due to the large surface energy. It may be due to the spatial confinement and reduced imperfections. So there are various reasons which are responsible for the improved properties of the nanomaterials at nanoscales. But anyhow, as I told you, it depends, vary from material to material, but in general we can say that it is the large fraction of surface atoms, large surface energy, the spatial confinement and reduced imperfections are some of the basic reasons that are responsible for the improved properties of the nanomaterials. Let's come across some of the properties that why it's improved. If we have the reduced melting point, the nanomaterial may have significantly lower melting point or phase transition temperature, and a appreciably reduced lattice constant, that is actually between atoms. The spacing between the atoms is reduced. The lattice constant has been reduced due to a huge fraction of surface atom and the total amount of atoms. Because this size is really interesting, the number of surface atom increases, and that lead to decrease or reduction in the lattice constants. The second thing is that these materials are ultra hard. Its hardness is very high, because and hardness is one of the mechanical properties. So the mechanical property of nanomaterial are close to the theoretical strength, which are one or two order of magnitude higher than that of single crystal in the bulk form. So this enhancement in mechanical strength is simply due to the reduced probability of defects. So this is one of the reasons why its mechanical properties are improved, that the number of defects are reduced. The optical property of nanomaterial are really interesting and improved compared to its bulk crystals. So it might be due to the two reasons. One of the reason is the semiconductor blue shift, that is the absorption and emission due to the increased band gap. Due to increased band gap, this is called as a quantum size effect, or maybe in some cases the band gap is reduced and the absorption capacity of the material is improved, or in some cases we have a particle in a box that is also improves semiconductor blue shift. And we have metallic nanoparticle that color changes in spectra due to surface plasmons resonance. So this is one of the example from Lorentz oscillator model. So the other is the electrical conductivity, which decreases with the reduction dimension due to increased surface scattering, and the electrical conductivity increases due to the better ordering and ballistic transport. The magnetic property of nanostructure material are distinctly different from the bulk materials. The ferromagnetism disappears and transfer to super paramagnetism in the nanometer scale due to the huge surface energy. And some of the other reasons are the self-purification in an intrinsic thermodynamic property of nanostructure and nanomaterial due to the enhanced diffusion of impurity or point defects at the nearby sites. So that lead to the increased imperfections, enhancing chemical stability, and as a result the number of defects or the defects level has been reduced, which improves the property of the materials. Let's come toward the we have discussion regarding the melting points and lattice constant changes when we reduce the size of the materials. So let's consider the nanoparticles of metals or semiconductors or molecular crystals. If a size is less than 100 nanometer, then we have a lower melting point, and the difference between that is around 100 degrees Celsius, and as a result of this there is also a reduction in the lattice constant. So what is the reason for this reduction in the lower melting point and the reduction in the melting point and reduction in the lattice constant? It might be the surface to volume energy ratio that changes dramatically. And what is the reason to get off, or the surface atoms or volume, the surface atom increases, and it greatly improve the property of these materials. So melting point and lattice constants are further clarified in these slides. As we have atoms or molecules on the solid surface that possess fewer nearest neighbors of coordination number and thus have dangling or unsatisfied bonds exposed to the surface. So because of these dangling bonds on the surface atoms or molecules are under an inwardly directed forces, and the bond distance between the surface atom or molecule and the subsurface atoms or molecule is smaller than between the interior or the bulk molecules. This is really interesting, and this is one of the crystal defect, that the atoms of the surface are different, or different forces are applied on the surface of the atom as compared to the bulk atom. Because if we consider the coordination number, or the number of nearest neighbors to an atom that is present in the crystal, that there is a break on the upper surface, so the atoms are stretched in the inward directions. So when solid particles are very small, such decrease in bonds length between the surface atom and interior atom becomes significant, and the lattice constant of the entire solid particles shows an appreciable reduction. So this is one of the reason that because of the surface changes and the number of atoms reduce greatly when we go toward the smaller size. So and due to the surface, the behavior of the surface atom is different from the behavior of the bulk atom. So that is why we have this thing that is changes properties. So the surface free energy triggers reconstruction, and this is one of the example of silicon 100 reconstruction, that is 2x1 surface. So this is an example of it. So this is the melting point stabilization by reducing the surface free energy using SM. This is one of the example. If we reduce the surface energy, there is reduction in the lattice parameter of CDS nanocrystal as a function of the reciprocal particles and of the radius. So here we can see the atoms that are squeezed together and the atoms that are comparatively are slightly relaxed. So we see that the properties are greatly changed. Here is the lattice constant on the vertical axis, and here is the lattice. This is the lattice parameter, and this is the size of the atoms. I mean the size or the distance between the atoms as a function of reciprocal particle radius. This is the reciprocal particle radius on the horizontal axis. So as a result of that, there is a great reduction in the property in the lattice constant. So this is one of the reason for its improvement. So the mechanical property typically improves. If we go to the mechanical property, then the mechanical property of the nanomaterial typically improves, and this calculated strength of the perfect crystal exceeds that of real one by 2 or 3 order of magnitude. So what is the reason for that? Much work has been done on whiskers that approach the theoretical limit first demonstrated by Herring in 1952, and the diameter of that is less than 100 micrometer. So this enhancement in the micrometer scale, which is different from the size dependent properties. So two possible mechanism has been proposed to explain the enhanced strength of nanowires or nanorod that are actually in reality sizes less than 10 microns, and one of the reason is the increased internal perfection, and the second one is the increased surface perfection, as we discussed in the earlier slides. That was the actually increased internal perfection leads to less number of defect, while increased surface perfection leads to the stretching or the bonds that are present at the surface. So the number of atoms reduced, so it is greatly contribute to the properties of the material. So the mechanical properties are further shown. We have photoluminescence of one of the materials, size is 150 nanometer. We have the whiskers of that. I mean the small cross section of whiskers are nanowires, and the less is the probability of finding it in any imperfections, that is dislocation or microtwins, impurity or precipitates, etc. So thermodynamically, the imperfection in crystals are highly energetic and can be eliminated. Just a small size makes such elimination of imperfection possible. So imperfection in bulk materials such as dislocation are often created to accommodate stresses that are generated in the synthesis and processing of bulk material due to temperature gradient and other inhomogeneities. And some of the other reason for that is that the stresses that are generated in this case cannot be excluded, but are generally not as likely to exist in small structure, and that is particularly in nanomaterial case. So these are the mechanical properties of the materials, that how the mechanical properties are changed with the help of when we are coming toward the reducing the size of the materials. So what happens in general, smaller structures have less surface defects. I mean that is one of the reasons that it have less surface defects, and it is particularly true when the material are made through a bottom top approach. So this have less surface defect, and vapor grown whiskers with diameter of 100 microns or less had no detectable steps on their surfaces by electron microscopy, where irregular growth steps were revealed on whiskers with diameter about 10 microns. So both mechanisms are closely related, because when a whisker is grown at a low supersaturation, there is less growth of fluctuation in the growth rate, and both the internal and surface structure of whiskers are more perfect. So here in the figure it is shown that there is some relationship between the strength of the material, and that is actually the typical dependence of strength and the diameter of sodium chloride whiskers, and similar dependencies are found in metal semiconductors. So we see how there is a relationship here in this figure, the strength and the diameter of the material. So how the strength is reduced when we increase the diameter of the materials, and when we go through the lower diameter size of the nanomaterials of the diameter of the materials, the strength drastically improves. So in the last few years, IFM and TM have been applied for measuring the mechanical property of nanowires or nanorods. So both IFM and TM promise some direct evidence of the mechanical behavior of nanostructure and nanomaterials. So all these things is because of the increased surface perfection, and what we say that increased surface perfection is nothing but actually it's the increase in the the reduced amount of defects in the materials. So this is something about the mechanical properties of the material, how the mechanical properties are changed when applied. Here is a curve that is between the strength and the diameter of the material, and we want to know the relationship between the strength and the diameter of the materials, and it could be explained with the help of lower grain size. So we have the micrometer size grains, and the Hall pitch model that is treat again the grain boundaries as a barriers for the dislocation motions. So actually the grain boundaries are the barrier or obstacle for the dislocation motion, and the plastic deformation is caused due to the motion of dislocation. When dislocation are pinned at the grain boundaries, so it drastically improves the strength or the hardness of the materials. So upon reaching a critical stress, the dislocation will cross over the next grain and induce yielding. So the yielding only occurs when we drastically improve the applied load or applied force. So it means that as a result of this grain boundaries, the dislocation motion is stopped or it is hindered. So when the dislocation motion is stopped, so as a result of that the properties, this strength of the material improves. But if we further improve the external load or the force, so it may be there is a brittle fracture that lead to the yielding of the materials. So the Hall pitch model says that the smaller the grains, the stronger the material is. This is one of the model that has been introduced, and according to this model, it has been known to us that when the grain size is smaller, then the material will be stronger. But there is no such relationship because it's vary from material to material, but that was the general relationship developed by that model, and that is not valid any that is not for all cases not valid, but it generally is that if you reduce this grain size of the material, the properties or the strength of the material improves, and that is due to the the hindering of the dislocation at the grain boundaries. So we have some nanostructure reactive materials, and that control the chemical and physical properties of hierarchical material structure that contain nano-sized components, and it's control and optimize the material property and chemical reactivity. What we use is the nanomaterials are widely used in different aspects of life, as we discussed in the beginning of the lecture and in this slide again. It is used in catalysis fuel cells, that is and even in bioprocessing and wastage reduction in chemical industries, because the nanomaterial are widely used for the environment, for the renewable sources of energy. I mean, the TiO2, we have used this TiO2 for degradation of inorganic material from the water that is coming from the industries. I mean, the wastewater, for the cleaning of the wastewater, and the same material has been used for the water splitting. I mean, that is the generation of hydrogen from water. This is a really interesting work because it can hydrogen is an energy source for us. So we have inexpensive photovoltaics and another energy conversions devices. That is the application of that, and it has highly selective sensing materials that is only possible with the help of improvement in the property of the material, and that could be caused by the improved reduction in the size of grains of the material, that is the nanomaterial. And we have structure. I mean, the structure of the material is optimized for energy transport. So we can tune the nanomaterial physical and chemical property by tuning the by arranging the atoms with inside the bulk or at the surface of that material. The structure place the structure in appropriate hierarchical environment. It can greatly improve the property of the or tune the property of the material, and we can integrate structure into mesoscopic and microscopic system, and from that we can develop the theory and computation approach to predict the properties. And that is really interesting for us because with the help of this we can improve the property of the material. So this was some introductory lecture about the properties and application of semiconductor material. I hope we have some more lecture regarding this topic. Thank you very much.